We're going to first look at motion in one dimension, and then we're going to see how this is going to apply to free fall objects, and then motion in two dimensions. But we're going to start off simply with motion in one dimension. In mind, let's go. This is the chapter introduction in your textbook, and you should be watching these lectures or listening to these lectures and checking them out before you dive into the textbook, so at least you have some kind of background into what you're going to be reading and taking notes and checking out what's happening. So here again from chapter 1, if you recall, describing motion. So there are your point particles, and here is your vectors in between, and since these are green, these are velocity vectors, and it shows how it corresponds to a velocity time graph down here. So here are the point particles moving through time. Here is your velocity time graph, and in this case it's showing that this particular car right here, the acceleration is 0 because these velocity vectors are the same. So it's constant velocity. All of a sudden the vectors are getting smaller and smaller and smaller and smaller and smaller, and that means the car is slowing down, and that means the acceleration is facing to the left direction, the negative direction. If it was speeding up, the car was speeding up, the acceleration vector would be heading to the right, but it's not, it's slowing down. So let's look at the correspondent graph down here. You're going to see a lot of this having to match up these point particle representations, and you draw them yourself, and then you do the graph, corresponding graph. So you can see there's a line dropped here, and that lets us know the difference between the constant velocity, and that's represented by a flat line on a velocity time graph. You really have to pay attention to what kind of graph you're using or that you're dealing with. Then right from here, you can see that it's heading down, 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 and the velocity is decreasing. You could say, oh, it's 5 meters per second, 4 meters per second, 3 meters per second, 2 meters, 0 meters per second. So the car is slowing down. So velocity, we've talked about that before, but now we're looking at specific definitions, and we're rolling in acceleration, some of the equations that we're going to use to describe velocity, and then acceleration. So analyzing motion, we're going to be given different situations, different scenarios, and we're going to have to decide well, what physically is going on. So it'll test our skills and especially our conceptual knowledge of what's physically happening in the situation. So we have a lot of tools for helping to analyze motion, and you've read about them already in chapter 1, some of them, and then we'll work on those in class together as well. So constant velocity, when we start off looking at one-dimensional motion, we're going to start looking at it with no acceleration. In that case, constant velocity is just that. It's velocity that's constant. And acceleration, there's no speeding up, slowing down. A lot of times we call constant velocity uniform motion. Now, constant acceleration, not to be confused with constant velocity, is the change in the speed or the velocity of an object, and we're going to come to find out that acceleration has to do with speeding up, slowing down, or changing directions. So acceleration changes velocity. So uniform motion is not in play here. Things are speeding up, slowing down, changing direction. So we call this a special case of motion, and we call it constant acceleration. So when you hear the word constant, you got to check out what the second word is, because if it's velocity, you're looking at uniform motion. So details will help you figure out what's happening in the situation. So free fall, it's a special case of constant acceleration, and this that we experience here on Earth. Gravity is a force exerted by our Earth due to the Earth's mass, and we end up having a certain acceleration as long as we're, well, not even if you're in the space out there in the International Space Station, the magnitude of gravity that we use for acceleration here, things that are close to the Earth in free fall, is 9.8 meters per second squared. So anyways, we'll be taking a look at problems in free fall. We experience free fall every day. So it's a familiar experience, but calculating a lot of different pieces that are under the influence of gravity. We'll be using free fall. So representations, so we have multiple representations of what's happening in a particular physical situation, a student walking to school, and you can see we're using the same tools here, the point particle diagram and table of data down here, and then we graph it. You will be responsible for looking at this and talking about what's happening with the student. You're going to have to be well versed in this and how to get to this point particle diagram to get to the graph. This happens to be a displacement time graph, and then over here your data table with the information that's used to graph here. But we can use all these different representations to show the same thing, the student walking to school. Okay, so this example problem, this is a spicy problem right out of the gates. And the first thing you're looking at, okay, I got a position time graph, all right, terrific. The next thing you want to ask yourself is, what does a line on a position time graph represent? And it represents velocity. So why does it represent velocity? Because the slope, so here let's look at a slope here. Along A, I draw a tangent to the curve. So the slope, as we know, is rise over run. And in this case, the rise, which is our y-axis, is our x. So you look at that. And then our run is our x-axis, so rise over run. And here on our x-axis, we have a t for time. So when you look at the slope of this line here, when you get the slope, you can imagine it's an imaginary ruler here. And boy, using a ruler is going to save you on these. You need to be having a ruler in your hand at all times when you're dealing with these graphs, because the slope of this particular spot at point A gives us the velocity at that point. You could also use the term speed. Speed is a scalar quantity, and what a scalar quantity is, revisiting, it's just a magnitude. Velocity is a vector, so it has magnitude and direction. So not only does the magnitude of the slope of this line matter, so does the fact that it's a positive slope, and that would tell us the velocity is positive. So if you were just concerning yourself with speed, all you have to do is just look at the magnitude of the slope. And we're not going to be having a lot of numbers on these graphs. So you have to get your ruler, you have to line it up tangent along the curve, and then decide what do you have. I have a positive slope, and it's quite steep right here. So I wouldn't be surprised if this is, because that represents speed, it's increasing. So if it's one spot, how can you say it's increasing? Well, what you do is you get your ruler, and you start here and you work your way along, and you know, oh yeah, wait a second, the ruler starts flattening out, and up at B, the ruler is horizontal. That's letting you know that speed is 0, because the slope of the line represents speed or velocity. So you would use your ruler, slide it along each spot, and from A here, you work your way up to B, then you work your way down this side of it with your ruler to D, you keep going, and you're finding the tangent at each spot. So you're going to be using this technique a lot, and your ruler is going to be your friend. All right, so let's see, take a look at this. At what point or points do the following conditions apply? Displacement 0, speed's increasing or speed's decreasing. All right, you take a shot at that on your own and take a guess, and then we'll go to the next slide and see what the solution is. So here we are, and what I've done is I've inserted the slope at each position. I know that's not perfect. I don't have a ruler. It's really hard to draw on these diagrams, these graphs, but that's okay. You get the idea. So the slope of an xt graph represents speed or velocity. So this is pretty steep here, and then it looks like the car is really going fast, and all of a sudden the slope is getting less and less. This car's slowing down through A and B. Right here where your ruler is horizontal, that lets you know that the slope is 0. That means velocity or speed 0. And that would be point B and E because the same thing occurs over here. So I'm pretending like this is your ruler, your blue, that blue line I've been drawing there, tangent to the curve. So B and E is the answer for the speed is 0. So the displacement is going to be 0 at that moment in time. If you're not moving, you're not displacing. So if the car is not moving at that moment in time, there will be no displacement. So B and E are the answers for the first two. Now for C and D, you have to look at the kind of what's happening throughout A as you move the ruler. Even though this is a static presentation, you can imagine I have my ruler here and it was steeper here. So now it's less steep. And if I go here, it's even less steep. So the speed is decreasing through A. When you look at this, you're like, well, right at A, what's happening right at A? That's it. That's the speed or the velocity right at A. It certainly is. But what you're looking at is what's happening to the speed from before A to after A, and that's what we mean by the speed's decreasing because the slope of the line's decreasing. When you look at C, the slope of this line from here to here is increasing. So whenever you have a ruler here, you can see it be flatter all of a sudden, like almost not totally flat like this, where there's no speed or velocity, but right here, and it gets steeper and steeper and steeper. And so at this point, your speed is increasing. And a lot of students will say, well, Miss Eisenhower, the slope is negative over here. Negative is your direction. It has nothing to do with magnitude. And when we look at speed here, when it says speed is increasing, we're looking at just the magnitude, and the speed is increasing. So this car is speeding up in the negative direction. So just for giggles, you could describe the speed at D, and it would be negative and going quite fast. Okay. Please take a moment to read this tactics box. These are the tools that we've been using to read the position time graph, and I've talked about it, but you want to pause this and take a moment, not motion, to notice the things I've been saying are these points here, which are very important. You'll also find this tactics box during your reading, but the velocity on a position time graph, the slope represents velocity, so that whole ruler, use your ruler, will help you with all of these: direction of motion, the magnitude of the velocity. So even when there's not numbers on the graph, you would check the steepness of the slope. Maybe it's shallow, maybe it's really steep, and that'll let you know the magnitude without numbers. So direction and magnitude. And so if you would pause and read this for a moment, that would be terrific. Here's some practice problems. So try this one out, and you can hit pause. And I'm getting ready to forward the slide, or forward the slide, so you can pause the video for a second, and the answer is going to pop up on the next slide. But here's a tip. Make sure that you know it's talking about a velocity time graph. It's not asking about a displacement time graph. All right, here we go. Right here on this particular slide, so here's your answer, C, but let's see how we came about picking this answer. So this is how I would go about doing the problem. So here's our point particle diagram. I check my velocity vectors, and these three are equal, meaning equal displacement in equal increments of time. We have constant velocity here. Now right here between these particular measurements or time intervals, we have here's our velocity vectors, and they're all of equal size as well. However, they're double the size of this. So we have constant velocity for this half, and it's heading in the positive direction. We have constant velocity for the first half, and it's heading in the positive direction. So let's start off trying to match this up to a velocity time graph. So if velocity is constant, first off, we're smart enough to figure out, hey, if it's constant, here's the velocity, it's going to be a flat line. So our only choices are C and D for the first half of this physical motion for this car. Now, when you look at the velocity over here, this is 0 meters per second. This car is not sitting still, so that rules out D. So right off the bat, boom, you have your answer. It's C. Let's double check and see if the rest of it looks good. So we have a constant velocity. Let's just pretend like this vector arrow represents 3 meters per second. We know it's in the positive direction, and when you look at the magnitude or size of the vector, it tells you the magnitude of the velocity. Let's say, okay, these over here are double the size of this one exactly. So if this was 3 meters per second, this would be 6 meters per second between each time period. So when we look over here, this does match up. If this was 3 meters per second, we could just pretend like this is 0, 1, 2, 3 meters per second, 4, 5, 6 meters per second. So this is constant velocity in the first half of the car's motion, is for first half of the time period. And then we have double the velocity heading in the positive direction. So it is a flat line because it is constant velocity. If velocity was changing, you would have a slope like this here, here, or here. It's not changing, it's constant. So let's look at one other interesting piece here. A lot of students will, and rightfully so, they'll look at this situation, Miss Eisenhower, this is going 3 meters per second, this car, then all of a sudden, poof, it's going 6 meters per second. What isn't there? Doesn't the car have to accelerate in between 3 meters per second to 6 meters per second? Are we missing a piece here, or is it just some kind of crazy thing that happened on this transverse, this parallel universe, and boom, it's faster? No. That we do this because as we're learning the material, and we even have a straight line up here, it even looks, oh, it's instantaneous. All of a sudden, 3 meters per second to 6 meters per second. This is how we draw them. So no, you're not incorrect in looking at the situation and saying to yourself, hey, are we missing something between here, just for learning's sake and getting used to the diagrams? In fact, you usually won't see something in between there. They usually just use a straight line, and you are very smart and you know that this represents a certain magnitude and that this is double. So yes, physically there's something happening in between those two spots and we're not addressing it. So let's go ahead and move on. All right, try this one out. Go ahead and hit pause on your video, and I'll forward it in here in a moment. What I really like about this problem is that you go from a point particle diagram, motion diagram, to a graph. And this one, now they switched it up and they said, okay, now we're going from a graph to a graph. So you're going to have to go from a graph to graph, point particle to a graph. If you have a graph, you should be able to draw the point particle diagram. So let's take a look here. So this is the displacement time graph, and it's a basketball player. All right, my favorite sport. So here we are. And let's say this, we're going to define this as 0 meters because it's at the center of our Cartesian coordinate system. And we're going to say this player is standing at a 3 meter mark, just 3 meters, just standing there. And I know they're just standing there because as time passes, they're still standing at the 3 meter mark. So what does that tell you? You're like, well, the player's not moving. So their velocity, because now I have to look at the velocity time graph that matches it, it's going to be 0. So with that in mind, we know that 0 is right here. 0 meters per second. So this could be a possible correct answer. This could be a possible correct answer. This could be a possible correct answer. So let's see why this is the answer and these are not. So first off, we go up here. The player, remember on XT graph, that the slope of the line represents velocity. This slope is constant and it's negative. So you're like, okay, I have my ruler and I put it on there, and yes, I see that the slope is negative and it represents velocity. Now you're not going to be able to get the magnitude. There's no number on there, and the majority of the stuff of the problems you look at in this course will be qualitative and answering questions conceptually. So we're looking at a negative velocity and it's constant. So this isn't the answer because it's a positive velocity that's constant. Over here, the velocity is changing, so that would indicate acceleration, so they're out. So C is your answer, and there's your negative velocity. All right, one more. I think this is the last one. All right, so try this one out. Go ahead and pause your video while you try to figure this out. I'm going to forward to the next one. So here's a solution for this particular problem. And we had to go from a graph to a graph, but this time we went from a velocity time graph to a displacement time graph. The first problem, I believe, was point particle to a displacement time graph, and then we went from displacement time to velocity time. So you have to be able to go easily between the multiple representations of motion. So this one I like, it has velocity time, and now you have to match it up with the displacement time. So first off, zero velocity is represented right here by the origin on your VT graph, 0 meters per second. Well, first off, we got to go up, meaning we're moving in the positive direction. So this is positive velocity here. So let's just pick a number, 3 meters per second. So this hockey puck is traveling constantly at 3 meters per second. So it's moving at 3 meters per second. It's uniform motion. Then all of a sudden, boop, it's going 0 meters per second. So it's stopped. So let's take a look at the graphs, the answer selections below, and see which ones match up with this, the first half of the graph, what's occurring. So constant velocity means that, and it's positive constant velocity. So the puck is displacing in a positive direction. So this one, the puck is sitting still. That's not the answer. It's sitting still here. Boom, not the answer. So A and C are out. So now we're left with B and D. So let's look at B and D. So yes, we can see that there's displacement in the positive direction for both of these, and that matches up exactly with what we have going here. Because if you have a positive velocity and it's constant, that means that you're displacing constantly in the positive direction. So you're going to have a slope that's constant, and this meets the requirement for both these. Now the second part of the second half of the event has the puck sitting still, meaning zero velocity. So you read it here, zero velocity, which is 0 meters per second. It's not moving. So it's not moving. That means the displacement line on the graph is not only it's flat and it's horizontal. So, but I like what they've done here. They've made it a little more interesting for you to be able to discern between these two pieces here. So why is D the answer and B is not? Well, first off, the puck got to a certain point because it was moving and then just stopped moving. So when you look at this, you're like, yeah, it got to a certain point and it just stopped moving. So it remains at that position. So this is just remaining at whatever position would be on the x-axis here. So it's moving in a positive direction, and now it's 0 meters per second velocity, so it's just sitting there. It's not moving. Now look at over here. This has a flat line here, so it's not moving there either. But whoa, this is the piece that makes it incorrect. So what's happening here? They're trying to see if you go for the fact that this is just dropping straight down, and they're looking for students that are just going to buy into, hey, this is dropping straight down, so this is straight down, this is straight down. This has got to be the answer. So they've made it a little trickier where you've actually had to determine, so what is this line dropping down here? What does this mean on this XT graph? So in this particular case, let's just pretend like this is 0 meters. And since the puck is moving away in a positive direction at positive velocity, we'll say 1 meter, 2 meter, 3 meter, 4 meter, 5 meter. And now the puck's not moving anymore for the second half because we know it's 0 meters per second. But whoa, the puck miraculously has made it back to the 0 meter mark. To make it back to the 0 meter mark, you would have to have a negative velocity. That's not what's happening here. There's no this is the negative velocity area down here below the 0 meters per second. That's not what this graph is. It's just saying it stopped. So this is going to be correct. This is indicating an extra motion of the puck that did not occur. So they're just trying to see if you'll go for that. So, and if that happened to you, don't beat yourself up over it, but just be careful and read it for what it is, piece by piece. You don't want to just look at a picture and say, that picture looks like that and that looks like that. They must match. No, 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 no. You have to read a graph bit by bit for the pieces that they give you. It's not a picture that just matches. It's in a concentration game like when you were a kid. So you have to be careful and take your time interpreting the graph. So in this case, and it stops here, and the puck stopped wherever it was located. Let's just say it was 5 meters, and it just sat there. But here's another point, and this is the last point I'm going to make. This puck, they just said, hey, let's start the puck at 0 meters, because you can see it's at the origin of this coordinate system, and it heads up to 5 meters, and then it's sitting still here. Would this graph be correct if we took the same shape, this line up to the right and this flat line, and just shifted it up? Like the puck started at 3 meters, and then it went up and it made it to 8 meters, and then it sat still at the 8-meter mark. Would that be a correct answer? It most certainly would be. So yeah, the shape of the graph is correct, and we could move it further up, and we could even move it down. As long as it has this shape, that is the answer for this particular graph match for VT, XT.